Alright, welcome to hell. We're about to make this a whole lot more messed up than it currently is. So let's get back to drawing land for a second. Um, so we sort of treated these as two groups of commands. We did place and then we did left, right, and move as their own group of commands. But we did them separately. They were a group of things, but they're still separate. So that's what I was mentioning with so like this is essentially one thing. This is essentially one thing. This is one thing. This is one thing. It's easy to see that if you break it down like this, where left is one thing, right is one thing. These are all sort of discrete things. If you go with the logic of you have to have one thing per line, then this is not actually 4 lines here. This is 6 lines. Plus place, so it's actually 7 lines. It's left, right, move when we're facing north, move when we're facing south, move when we're facing east, move when we're facing west, and then place at the start. So it's a bit hacky. We could address this in several different ways. Let's start with welcome to my graveyard, by the way. This is an enormous amount of like code of all of my failed attempts. So let's go through. God, there's so much code. Let's start off with cleaning up some of the code. So, for example, we can change this from a tuple that's called state with unnamed, I don't know what these are called, fields, properties, items. Instead of that, we can name each of those things. So we can actually, instead of doing state dot item 1, we now do state.x, state.y, and state.direction. And that's just a lot more intuitive. There's also some code we had here related to math absolute. Some early versions of my submission actually used negative numbers as part of the process, but then I simplified it to just use positive numbers. So I no longer needed absolute. We never deal in negative numbers except if the robot is not placed. So we can cut all of that out. There's a few other minor things like that where the logic hasn't really functionally changed, at least not in a way we care about. And that lets us simplify things down a little bit further. One of the things that you can also do is, instead of using if and else if, you can lose your mind and use ternary operators. And that's what some people did. So this is an example of that, and I'll just unhighlight that so it's not in the way. And hopefully you can actually see this code. If your monitor is really small, I'm sorry, you're going to have trouble reading this, but there's so much to fit on the screen. So a ternary operator is, we can, instead of doing an if-else like this, we can format it on one line like this. So is 2 greater than 1? If it is, then test will equal it's greater. And if it's not, as symbolized by this colon, that's like having the else, test will equal it's not greater. So, I mean, this is saying it's unreachable code because obviously 2 is always greater than 1 unless you have like a cosmic ray flip your bits or something. But the premise is there. So instead of doing an if, blah, else, blah, you can use ternary operators to inline everything. If you do that for every if else that I have, you can put it all in one line. And so you have, and you can also, as I showed before, you can condense the variable initialization such that you have the string input initialized or declared and initialized on the same line as the state. But hey, if you're gonna do that, if you're gonna like just throw it out the window, sensibility out the window, why not just put everything on one line? Visual Studio with its default parameters, at least in Visual Studio 2022 on Windows, it'll let you. It looks gross, but it'll let you do it, and that's technically one line. Functionally, it will work the same, so it still fulfills the requirements, but it feels like cheating. Another thing that we can do is remove remove the description of state entirely and just start addressing these variables directly. So instead of addressing them like state.x, state.y, state.direction, which is sort of what we did in the original, we had state.item1, item2, item3, and now we've named the items. Instead of simply naming the items and then addressing them as parts of state, we can remove the name of state and directly address the variables. So that's another option. And then we get into the actually good stuff. So let's go back to the world of drawing. Let me show you a glimpse into hell. Coding hell. I think this is on layer 3. Nope, it's on layer 2. Let's move that out of the way. Actually, we can just delete it. No, let's move it out of the way, just in case we need it later. And we'll draw on a new layer with a nice wiggly line. Okay. So I mentioned before how we've treated these sort of as individual things, where left is one thing, place is one thing, right is one thing, move when we're facing north is one thing, move when we're facing east, west, and south. So we actually have 1 + 1 + 1 + 4 = 7 sort of unique commands or unique inputs that we have to handle. But hey, if left, right, and move all use the same parameters implicitly, why don't we find a value for t that the same way that we can do all of the directions for place at the same time? What if we find a value for t, a different t value, that lets us handle all of these at the same time? So how the hell do we do that? Let's quickly hop back into the code. Somewhere up there I have it. Okay, so instead of pulling, this is probably easier if I draw it instead of show you the code. Instead of pulling the first digit of hash result, which is what we were doing before, where hash result could be, or the first digit would map to these. It would be north, east, south, or west, just in quantized integer form. What we can instead do is have hash result 0 always be, for example, how far east we want to go. So this would be, we'll call it eastward, equals the first digit of the hash result. And then I'm going to glance back at my code. If we, for north, we can go northward equals the second digit of the hash result. If we want to go south, and bear with me for a moment, if we want to go south, we'll get the fourth, not the third, but the fourth digit of the hash result. If we want to go west, we'll get the fifth digit. And then if we want to apply a turn left or right, and remember that our turn is always +3 or +1, we will get the third digit of hash result. And so instead of having a hash like this, where we only actually end up using the first digit, we're now extending the usage of the hash to 5 digits. Such that we could, the simplest way, definitely not the easiest or most efficient way, and I'll talk more about the lack of efficiency as we go. The simplest way would be, so this is 0, God, I can't draw, 0, 1, it's also really cramped, 2, 3, and 4. We make it so that the index 0, if our input is, if our command input is east, I need to draw more things. If our command, I'll just make it smaller so it will fit. Our command is not east, because east is not a command, but our direction is east. And the command is move, which should be in blue. Command is move. Then we want this first digit, because the first digit is representing how far east we want to go, is going to be 1. So that if we have exactly these inputs, we can just say, take x and add 1 to it. So we want to find a hash where that's 1. The problem with this is that although it's possible, we have to have a lot of conditions simultaneously satisfied if we just want exactly 1. Because what we'll need to be doing with this arrangement, where eastward is this, and this is northward, this is the turn, this is south, this is west. If our inputs are move and east, we need this to equal 0, we need this to equal 0, we need this to equal 0, and we need this to equal 0, just for this combination of inputs. So we have this quite difficult set of conditions to meet. But then the problem becomes, if the command is move, and the current direction that we're facing is west, we don't want east to have a value. We don't want it to be 1. We want it to be 0. We actually want, in this case, the 5th value to be 1. We want this one to be 1, not 0. And we need all of these to still maintain their 0 state. And so all possible combinations is move east, move west. Well, move when we are facing east, move when we are facing west, move when we are facing north, and move when we are facing south. But then because we need to feed in the state as the parameter for the hashing, we end up in a situation where left, instead of only caring about the fact that we're left and that's it, because normally when you turn, it doesn't matter which direction you're facing. We always, every time, we +3, and if we turn right, we always, every time, +1. Doesn't matter if we face north, doesn't matter if we face east. It's always the same thing that we're doing, the same action we're taking. Unfortunately, if we feed the state in, we have to also control it so that the state for left doesn't influence what we don't want it to influence. So even though left is not a move command and we don't want to move because we don't want it to move, we have to make east, north, east and north, these first 2 digits, as well as west and south, those last 2 digits, or south and west, those last 2 digits of this 5-digit section of the hash. They must always be controlled to be 0 if we want to use a simple assignment like this, where we don't want to have to process what's coming out of this. We want it to just throw it in unprocessed by finding that magic number t that will let us do something like what we did before, except instead of 4 possible things that we need to control for, we now have 12. Because it's left when we're facing east, left when we're facing west, left when we're facing north, and that for south as well. And then it's also for right, excuse my writing, right times 4, because it's going to be the 4 directions again. So that equals 12 possible combinations we have to worry about. And for every single one of these, we need to control for 5 numbers. So if you think about how complex or how many iterations you might need just to get a couple of these done, and then realize that each time we add another, we're making it exponentially less likely to find the successful hash, you end up with an enormous number of hashes that you have to look through. And if you have a supercomputer, you could probably do it. You can probably just brute force it. I have a reasonably powerful computer, and I hashed roughly 1 quadrillion MD5 hashes, and I could not find a value for t that gave us this extremely unlikely hash result, which satisfies all of these conditions. And that is even after I parallelized it. So if we jump back into our code, the original code with the hashing, this is all running on 1 thread. So it's not making use of a multi-core processor, a multi-threaded processor. In my follow-ups, I realized that was a problem. And so I learned some basic parallelization of the hashing so that my 16-core 32-thread processor can actually like do things faster. And I hashed, like I said, I hashed like a quadrillion things. I'm not exaggerating, like a quadrillion things, which is like the next 1,000 up from trillion. And I could not find the number. So we need a different approach. This simplistic approach of hoping that we find exactly the number we want so that we can very naively just add it in, it's too difficult to find that. We're all going to be dead before that happens if I try to do it on my computer. Again, supercomputer could probably brute force it, but a regular computer, no way. I don't think so. Yeah, the probability is just too low. If you get lucky, of course, that might be enough, but you can't rely on luck. So there's several ways to speed up this process in order to find that magic t value which we need. One of them I already talked about is parallelization, where we hash multiple things at the same time, multiple potential candidate t values at the same time to see if they have the result that we want that matches all of these conditions. So that speeds it up quite significantly if you have a pretty powerful computer like I do. And on that note, actually, I'll just pull something up for later. It's just taking a while to load. Alright, I'll have something that I'll try to include later. But for now, let's go back to what we're talking about here. So parallelization, another thing you can do is you can make the hashing algorithm more efficient. So before we were using MD5, which is quite fast, and it's not cryptographically secure by modern standards, but there are hashing algorithms that are faster than it. So one of the things that I first tried to do when I was looking at ways to speed up my code was I started using a hashing algorithm called XXHash, I think it is. Yeah, XXHash. Oh, sorry, I didn't have the code on the screen. Let's bring it up again. Called XXHash. And that's available from many places. It's not like owned by Microsoft or something, but Microsoft does offer a NuGet package called microsoft.system.io.hashing, which includes XXHash. So I used that. And although XXHash is actually quite a lot faster than MD5 hashing, it actually didn't help all that much, because the main thing that takes time in each of the times that we're calculating a potential hash result, like a candidate t-value, we're looking for a candidate t-value by hashing all of this stuff. The main thing that slows us down is all of these checks. So even if we improve the speed of the hashing, it afterwards, when it's checking all of these values, that still is taking up a huge amount of time. So the next thing we can do is make each of these more likely to succeed. Each of these individual checks. So when we're looking for that first value to equal 1 for this set of inputs, how can we make that more likely to succeed? One way to do that is to modulo 2 this number, which means that because we only ever want the value to be 1 or 0, right? If we have the whole range of numbers 0 to 9, then any given number has a probability, if the hashing distribution is even, which is a bit technical, but if it's even, and for simplicity's sake, we'll assume it is, the probability of any single digit is 10%. The probability of getting 0 is 10%. Probability of getting 1 is 10%, which makes you start appreciating how insanely difficult it is to get all 5 of these correct, and then again 12 times. The probability is very small of getting the hash that we want, the hash result that we want. So if we modulo 2, we crush this range down into a range of 0 to 1, and now the probability of getting either result isn't 10%, it's 50%. So we've increased the chances substantially if we modulo 2 this number and then check if the result is 1 or 0. And modulo is a pretty fast operation generally to perform. So that should be increasing the odds by 400%, because we're going from 10 to 50. This should significantly outweigh the cost of doing the modulo 2 operation. But that's still not enough, because for those who have completed SIT, I think it was 221, data structures and algorithms. It might have been 223, I don't remember. But data structures and algorithms, remember big O and big O notation, where I don't remember the exact syntax anymore, just the ideas. If you have, let's say, 5x to the power of y, if you change, well, actually to the power of y plus 3, let's say. If you change this plus 3, it doesn't matter that much. The thing you actually want to change is y, and the thing you actually want to change is x, not these sort of peripheral values. You're most interested in changing stuff that changes by orders of magnitude. And even though 400% is pretty good, it's not an order of magnitude better. So even with this optimization, it's not enough. We can do a little bit more here to make it a little bit better. So instead of having 50% 4 times, something we can do is we can make it so that because east and west are opposites and south and north are opposites, we can compare the eastward value minus the westward value. And specifically, it's these values. No, it's just those values. And then we add the result of those to our x coordinate for the robot. And that means that instead of having a 50% chance of hitting the number, it can now be 9 minus 8, or it could be 8 minus 7, and so on. If we combine that with the modulo 2, the odds are pretty decent of finding a result that we want. Not amazing, but decent. But like I said, this is still not changing orders of magnitude. You'll be sitting there hashing so many numbers looking for this, because the main problem is that this is 5 numbers long, and then this is 12 inputs deep. There's just too many, there's too much exponential growth in the amount of work that needs to be done. Changing some stuff on the margins helps, but we need to change it by an order of magnitude. What can we do? Let's think about what these commands actually need. So looking again at this little map, if we have a move command, we must know what our x and y are in order to know if we're at the edge of the map. And we must know what our direction is to know which direction to move in. So move needs all of these parameters in order to succeed. Left and right don't. So there is a way to compress these 12 states with these quite complicated, difficult to succeed, or unlikely to succeed hashing. We can compress those 12 states down to 6, where we have these move commands will stay, these move, I don't know, move states, I don't know what you want to call them. With move east will stay on its own, move west will stay on its own, move north will stay on its own, move south will stay on its own. But we'll compress left and all combinations of direction into just one command, one state, if you will. One input, I don't know what to call it. So this will all be compressed down to left. All of the rights, well, okay, not this part, will be compressed down to right. And then instead of 12, we'll end up with 6. And the reason this is so important is because this is essentially a single step divide and conquer. Again, calling back to data structures and algorithms, where instead of doing, I don't want to call it x because that's confusing. Instead of doing a to the power of 5 to the power of 12, which is basically what we're doing. Well, maybe not literally actually, but the 5 is these 5 numbers, the 12 is these 12 things. Instead of that, we can push it down to 6. Oh, well, actually, the way to represent this is probably 5a to the 12 versus 5a to the 6. If we can do this by compressing this stuff down, it is literally 6 orders of magnitude faster. 6 orders of magnitude more likely to succeed and find a number before we all die of old age. How can we do that? Well, the solution to how do we do the place was hashing. The solution to how we can compress these 12 things down into just 6, a solution is also hashing. So let me pull up the code. And we'll go back to my graveyard of failed attempts and successful attempts. And I will find for you, somewhere in this mess, the code that we're looking for. Here we have crunch commands. This is what we're looking for. So this at a glance looks kind of bad because we're actually doing 12 checks. But the reason it's not as bad as before is because each of these checks is simplified. We're not checking for 5 numbers anymore. We're just checking for this first digit in the hash result. So we have left and each direction encoded as a string, right in each direction encoded as a string, move in each direction encoded as a string. We're looking for a hash with a first digit with this input and 2 magic numbers in this case, so 2 T values, where whenever it's left in any direction, we want that to equal 1, right in any direction, we want that to equal 2, but then move in any direction, each have their own individual outputs. And we compress this range down using modulo 7. It's the same thing I mentioned before, where if we can compress this range down, that's good. And the reason that we've compressed it by modulo 7 is because there's 6 different options. And the reason I haven't used 0 as an option is just an artifact of XX hash. XX hash doesn't have leading zeros. As far as I can tell. I haven't used it very much, but it doesn't seem to have leading zeros. So it's very rare to find 0 compared to other numbers if you're looking at the first digit. So we start at 1 instead. And by crushing modulo 7, oh, sorry, I didn't have the code up. So the first digit can't be 0. So we don't want to use 0 as the output that we're looking for. We'll start at 1 instead. And by using modulo 7, we crush down the range and make this and this more likely to appear. This doesn't get changed because it's modulo 7. It doesn't crush it very much. But it means that if we find 1 or 8, this will succeed. If we find 2 or 9, this will succeed. So this is now twice as like each of these is twice as likely to succeed now that we're doing modulo 7. And we then apply modulo 7 to this bottom section just for consistency's sake, because it does matter. So we loop through I and j such that I and j are the T magic numbers that we're looking for. We feed in the command, we feed in the direction, so we basically are feeding in the state. And we crush that down from 6 states into 12, from 12 states into 6. Then, with our reduced state, we can go back to this, and instead of having 12 states, we can do the same thing, except we can do 6 states. And so I've already run this before, and both of these are actually they don't take that long to crunch. Before I had to get that quadrillion result, I had to run my PC for basically an hour, not an hour, like a full 24 hours, a full day, spread over several sessions, but a lot of time crunching numbers. Each of these that I end up using only takes a few minutes to find values that we want. So in our case, the crush commands, we need to input magic number of 9707 and a second magic number of 76111. and we need to format it like this where we use it. So where do we use it? That's a great question because I did this 2 weeks ago and don't remember anymore. I think we use it here, where so I mentioned before we have to convert stuff into bytes so that we can hash it, and then we have to convert it to strings and ints and blah blah blah. And I'm sorry I didn't have the code on screen. Doesn't really matter that much of this section, but so these are this 1, 2, 3, 4, 5, and 6. Those are these results here, where we have this second function which takes those as an input, and we're finding a second set of magic numbers, I and j, again. So these are another set of t values that match our conditions, where whenever we turn left and don't move. Whenever we turn right but don't move. Whenever we're moving north, we move north but don't turn, and we don't move on the x-axis. When we're moving east or west, the same thing, we move on the x-axis only, but we don't turn and we don't move on the y-axis. That's all the stuff that I sort of discussed earlier in the drawing world. And we can put that all together with all the magic numbers that we've found, and we can get this. And we've managed to make a very simplified, well, in some cases simplified, obviously in other cases extremely complex. But in terms of number of if statements we only use 2 if statements. We have if for the place, and then we immediately assign state using the hashes, and I'll show you that in a second. And then for left, right, and move commands all at the same time, we have one if that checks those conditions and then immediately assigns state. It's all done in one line. So what does that look like when it's unpacked? Well, the place I haven't unpacked because that's the same as before. It's actually using the same, I haven't recalculated the hashing or anything, it's just using exactly the same stuff as the previous solution, I should say. And then our second if, so this line is this line is this and everything below it. And you can see I have a whole bunch of like debugging code and everything, but you'll have to ignore because this is a wasteland of failed attempts. And debugging this code, as I hope you can imagine, is an absolute nightmare. Completely horrible, even with all of this debugging stuff that I had to add in. So if our input is left, right, or move, and again, remembering that our input is console read lines, so it's just what the user has typed into the console. If it's left or right, or if it's move, and it meets these conditions, and these are just checks for is the robot at the edge of the map. If it's not at the edge of the map, and it's one of these, we don't do this because this is a fucking console write line. This is all just debugging. We actually just do this. And so it's very difficult to read still, but you can see we have our magic numbers 4371, 9707, 76111, and 462151. And you can see the subtraction. So if we jump back into drawing land for a second, that's this subtraction here for east minus west, and then the same thing for north minus south. So our x is east minus west, and our y value is northward minus southward, which is the eastward is the first value in the hash, west is the fourth value in the hash, north is the second value in the hash, or hash result, I should say. And south is the third value in the hash. And again, this is pretty challenging to read. So I'll kind of break down a little bit more. We have this inner hash, and then if we look at where this terminates, that's over here. So we have this inner hash. This is the crushing the 12 commands down to 6. And you can see the same thing is repeated here, and it's repeated here, and it's repeated here. So earlier when we had this 1, 2, 3, 4, 5, and 6, that inner hashing is basically just if you copy pasted over this 1, over this 2, over this 3, 4, 5, and 6, if you just copied like this, the results of this, not literally this, but the results of this into there. That's what these are. Not those consoles. This. And we convert it to a string for the second hash. The second hash is this part down here, up here, followed by this part down here. So like we have the inner hash and the outer hash for eastward, for westward, for northward, for southward. And then direction actually has its own hashing thing. I won't get into exactly what's going on there. It's basically the same as what we've done here. Where you just control for the variables. So eastward, southward, westward, and northward. You just control those. My hand is like flickering in and out of existence. You control for those so that whenever you turn, you don't move. And so if you actually I have a this is an explanation of the old code, which would have been slightly easier to read, but it's too late. So I guess if you abstract away the details of this, it is basically static void abstracted string. This is essentially map size. Sorry, not max size, map size. Where we have, I mean, I should probably just copy this actually. Again, I'm not going to go into these lines here because we've already covered them. The new thing in this is the left, right, or move. So we have declare, assign variables on one line. We have while loop begins, and then we actually just have a curly brace, and at the end we'll also have another curly brace. And then inside the curly braces we have the if conditions for place, state equals blah blah blah, and then if conditions for left or right or move, then state equals blah blah blah. But within the state assignment, we basically have how do I explain this? If you abstract it away, we have x, y direction equals and so we'll put these all separately to make it a bit easier to understand. So x equals x plus minus something. And because it's a tuple, that's actually on the same part. So then we have y equals y plus minus something. We have direction equals this, which I guess I can explain now. This part is pretty familiar. That's just what we've been doing before. This thing at the end, plus the math max, I will briefly explain if I can find my notes, which I can. So I wanted to crush, I'll put myself back on the screen for a second. I wanted to crush, for our turning, we only care about values 0 if we're not turning. So that's if we have a move command, we want the value to be 0. If we're turning left, we want the value to be 3. If we're turning right, we want the value to be 1. So our range is 0 to 3, which is a range of 4, even though we only have 3 values, because we don't care about 2. So what we can do to optimize a little bit is a range of 4 lets us use modulo 4. If we can compress that down to a range of 3, then we can use modulo 3, and that's a little bit faster. So if you take the inputs 0, 1, and 3, you times them by 2, you minus 1, and then you take the max value of 0 and the result of this operation, well, these operations. You can remap 0 to 0, 1 to 1, and 2 to 3. And that's just a minor optimization of making it a bit faster to run the calculations. But whenever we do those optimizations, we have to also do them not just when we're calculating magic numbers, we have to do them again when we're using the magic numbers which we calculated. So in this example, the magic numbers of I and j were 249 and 219, 611. For x and y, those had their own set of magic numbers. You can see 4371 was I and 76111 was j. The outside hash, for the inside hash, the magic numbers were 9707 and 76111. Sorry, the outside hash had 462151. So just a great fun all around. But basically, this is outer hash command, which is input to string. That's what you see there. Command name, or actually we just call that. No, we'll just call it command name. That's good enough. Command name plus current direction. Well, actually, instead of plus, we'll just use commas. So these are all essentially being fed as parameters into the hash. So actually, no, this is as a parameter of outer hash, we actually feed in inner hash, which is the crushed one. So this inner hash is what crushes it down from 12 to 6. We feed that the command name and the current direction, along with those magic numbers. So we'll just do n1 is a magic number 1, n2 is magic number 2. So we feed inner hash into outer hash as a parameter, except we also add another set of magic numbers. We'll call them n3 and n4. So n3 is this is n1, this is n2, this is n4. And you can see those are consistent for all of the x and y stuff. So that's what we're doing each time. And y is the same, basically the same code. And because it's tuple, we have to do that. And the direction is, it's using a separate hash where we feed in another set of magic numbers. So we'll call those, I guess, N5. And then the command name and N6. And that's how we get X, Y, and direction. I'll run it just so you can see that it works. We have to switch over to 1.2 demo, and what is our main function right now? Our main function is currently using main. Oh, I guess before that, I can show you the crushed commands. So that'll take a little while to run. So I'll start it running, and then I'll just cut. And once it has a result, I'll come back. So it's still running. It's been like a minute or two. I just wanted to show. I thought it might tickle you to see what it looks like when it's just hashing numbers, looking for these magic numbers that we're looking for. So it's going wild on all 32 threads on the 16-core processor. And the clock speeds are a little low because unfortunately my cooler is not quite good enough for running something like this. But yeah, it's going pretty wild there. And you can imagine how much more work this is than if you just ran it in a single thread. Welcome back to hell. As you can see, the program is still running, but like 10 seconds ago, it found the magic numbers that we're looking for. So let me find a way to switch back the displays, because I want to keep that window up there. There we go. All right. So now I can switch back to Visual Studio, and you can see the numbers that it's spit out there. And as a reminder, that's running crush commands, which is this. It has spit out an I and J value, which I can't read. So I'm going to put that on myself again, which doesn't look any different to you, but does to me. You can see it spit out 9709 for I and 76111 for J, which is the same as what I already wrote down. And that's the same as what's getting used here and here. So that's the inner hash that I mentioned here. So that's 9709, and again, I can't read the numbers. 76111. That's N1 and N2. And I'm just going to stop that from running now because that's just burning electricity. If you're ever wondering what cryptocurrency mining is like, it's basically like that. Complete waste of electricity. And the outer hash would be running this. And so that was just running a few minutes to find the a set of I and J for the inner hash. The outer hash for memory also just takes a few minutes. And you can kind of estimate the progress that it was making through I and J based on what the numbers were. It's not perfect because I don't know how exactly the parallel 4 parallelization works. I don't think it's strictly sequential, but it seems close to sequential. So yeah, a few minutes of finding those magic numbers for the inner hash and the outer hash. A few more minutes to find the original place magic numbers. And then I'm pretty sure this is also a separate hash. I'm pretty sure that also just takes a few minutes. Because they're all reasonably optimized. I'm sure you could do better than what I've done if you maybe have a cryptography background or something. But yeah, so that's what I got. And if you put it all on one line, well, not one line, but like if you put it all in this structure, you end up with this, which is 1, 2, 3, 4, 5, 6 lines with no ternary operators, no messing around with multiple if-else stuff on one line. And we haven't even like cheated by putting the curly braces on like the same line as the code or anything like that. So that is the madness that took me several days. Instead of doing the assignments that I needed to do at the time, this was like 2 weeks ago. I don't know. I couldn't put myself out of doing this. I had a brainworm about the fact that I could potentially combine left, right, and move onto the same processing step. The holy grail would be finding a way to combine both of these lines, both of these processing steps onto one single line, which is definitely possible. It's just I'm satisfied with what I have. I'm done with the madness. I don't feel the need to descend any further into the depths. There's probably some optimization in the structure as well. I'm sure there might be something, like instead of a while loop, I know Max did a do while loop, which lets you have another logic check on this line here, which can be useful depending on how you structure your code. Maybe there's other stuff like that which you could use. But yeah, I'm pretty happy with what I've got. And one thing I didn't show you yet was how long it is. So I said before that my first submission, if you put it all in one line, it was like about 1750. This combination, because we have so many chained hashing, so much chained hashing going on, this single line itself is quite long. One could say rather long. It is 1848 characters long, if you include the white space at the front. So compressing everything down to one line without cheating has had a cost. This line alone is now longer than the entire thing on one line was before. And most of that is down to the fact that I did have to chain hash. I had to do like the inner hash and feed that into the outer hash just to find a solution in a reasonable time frame for those magic numbers that we've plugged in. But the result is something that's pretty short. It's pretty esoteric. I am pretty proud of the result. And I hope that you found that interesting. If you're one of the crazy people who spent something like an hour watching me go through this weird ass code which has no relevance to anything you're ever going to do again in your life. So take care. Hope you enjoyed. So real quick, just a couple things I wanted to clarify about what I said. When I went through and explained this step here with the east minus west and north minus... Oh, I don't have the right thing on screen. The east minus west and north versus south. That was not for optimization purposes as such. That was so that we could make use of east and west at the same time using a single assignment. So it didn't actually improve the odds compared to this. It's just that if you have two things and one represents east and one represents west, you have to have a way to end up assigning both of those one time, not one time separately, one time together. So that's why I did that. When I said I went through somewhere around 1 quadrillion hashes, that was true. It wasn't just MD5 hashes. Some of it was MD5, maybe even most of it, I'm not sure, but some of it was XX hash. And the main reason it was that fast and I went through so many hashes is because my first several attempts I was doing it completely wrong, and all of my comparisons were immediately failing. So I sort of cheated in terms of how long that took to run. The last thing is just I wanted to actually show the code running. So our main is main 5, because I don't think I did that. So let's get that running. I will... Is that the same thing? It is, okay. So it's running right now, but because there's no console output, we can't see anything. So what we actually need to do is stop it. We'll add debugging line here, like I had before. And so we'll hit that, and now in the bottom left, you can see all of the variables. We've initialized x, y, and direction to -1, and the input is null. So we have to continue, and then we can put our input in. So let's say place 5, 5 north. And you can see that we've now placed at 5, 5. And this is north because remember that our direction is running on modulo 4. So 48 is the same as 4, which is the same as 0. And that's north in this case. When I was running it through before in Drawing Land, I think I had it, yeah, north was 1. And that was true for my original submission. In the follow-up, I actually changed north to equal 0, which is why we ended up where we are. So if I pull up the thing again, so now we can, for example, we're facing north, so I have to continue. And then we can move, and you can see we've incremented on y. I have to continue again. We can move again. We've incremented on y again. If we, after pressing continue again, we can move left, and you'll see that our direction changes, but our x and y don't. And we can move right, and our direction will change again, but again, our x and y will not change. If we then continue a bunch of times, and we get to the edge of the map, and this is a 10 by 10 map, because that's what I fed into the arguments. If we try to move from there, it does not do anything. You can see that none of these variables are updated because we're at the edge of the map, facing the edge of the map. It won't let us continue moving. So it does work. It's a little clunky because it doesn't have a an output. You have to use the debugger to get the output, but again, that saves the line, so it's worth it.